One of the big questions that we have to ask ourselves when we're dealing with concentration data in an equilibrium situation is just simply whether or not we're at equilibrium. So we're going to look at something called the reaction quotient, which is kind of like a dipstick test, trying to figure out where we're at with respect to equilibrium. Do we need to move more in the forward direction? Do we need to move more in the reverse direction? Or have we hit the mark? A couple of the little details that we should keep in mind about our equilibrium constant is that just like in kinetics, we're not allowed to use any intermediates. So if we're dealing with a multi-step mechanism situation, we may need to be looking at substitution. More on that in a little bit. Just as in kinetics, all of these K values need to be determined experimentally. So there's a lot of different chart problems. We need to be looking at thermodynamic data. There's a lot of different considerations that go into the calculation of a K value. It's not always just going to be, let's take a look at the equation and write the information directly down from that equation. Just as in kinetics, that K value did vary with temperature, and because equilibrium constants are developed from the rate constants from kinetics, they're also temperature sensitive. We call that thermodynamically locked. Concentration data, though, doesn't seem to matter. It doesn't matter if you're dealing with high or low concentrations. A lot of the times equilibrium is pretty much set. That is a constant value, so that will always kind of shift back to that center point. Something else that you should know about equilibrium constants: not all reactions that you're looking at are always going to give you data that only has concentration data in it. So the state symbols kind of will tell you the tale. At this point, the only type of equilibrium scenarios that we've looked at have the state symbols straight across of AQ. So the only type of data that we can generate about those chemicals is concentration or molarity data, which is what the calculation of Kc requires. But that's not reality. Reality is that occasionally we may consume a gas or make a gas. Sometimes we will generate a solid or a liquid even. So we need to know how to handle putting in concentration data for these additional type of states of matter. So when we're calculating an equilibrium constant, I'm loath to say that the square brackets only represent concentration. The word that scientists tend to use is activity. Remember that Kc is really a dimensionless, a unitless type of number. So we're not constrained by unit agreement anymore. We can actually pull in a whole bunch of other types of numbers. So we call these things rather activities. And the activities of different types of states of matter will change. So for example, the activity of a pure solid or a pure liquid, you might be thinking to yourself, well, how do I know the concentration of a solid? It doesn't really have a concentration. Well, you're right. So in order for it to not affect our calculation of Kc, we plug in the value of a 1. Solutions are easy. Anything marked as AQ, you're simply going to plug in the molar concentration. Make sure that it's in molarity. And of course, for any gas, which they like to say is an ideal gas, although there is no such thing, we can simply plug in the partial pressure in ATM. This would be very useful in a mixed equilibria type setting. So something where you have an equation that has something AQ, something solid, something gas, all mixed up together in the same equation. Again, because Kc is unitless, we're allowed to mix together all of these different types of units. So now let's take a look at this dipstick test. How do we know whether or not we're even at equilibrium? There is this lovely little calculation called the calculation of a reaction quotient, or Q. Reaction quotient is calculated exactly the same way as Kc. The equation for it is exactly the same, but the major difference is that instead of being constrained to only plugging in equilibrium concentrations, we can plug in any concentrations. This will generate a new number that we can compare to Kc. And if it's equal to Kc, we know that we're at equilibrium. If it's any other value, we know that we're not, and that we would have to move in one direction or another to try and get there. And depending on the value that we get from Q, we can actually make the decision about what direction that is actually going to flow. So let's take a look at what this Q reaction quotient actually looks like. Let's take a look at this cute little equation. A plus B makes C plus D. And just like Kc, you'll notice that the equation for Q, the reaction quotient, is calculated exactly the same way, where you have the concentrations of the products above the concentration of the reactants. So let's just theoretically say that there's a scenario where C and D's concentrations are way, way huge. When you plug that into the calculation for Q, your numerator would be very, very large, which would make your Q value very, very large. So when Q is larger than K, what that means is that your reaction is product heavy. And in order to move toward equilibrium, you would have to generate more reactant, using up some of that product. So when Q is large, you move toward the reactant side. You move in the reverse direction. Let's say, for example, again, that you may have A and B, a lot of A and B, very reactant heavy. When you plug that into the calculation for Q, that means that your denominator would be very large, and that would reduce the value of your Q. So Q would be small in comparison to Kc. So when you calculate a Q and you find out that it is smaller, that means that you are reactant heavy and that the reaction would move in the forward direction to make more product and therefore reach equilibrium. And of course, the magical scenario would be if Q equals Kc, then you know that you have in fact reached equilibrium and the reaction does not need to move in either the forward or reverse direction any more aggressively to reach equilibrium. Let's take a look at an example problem. These are actually really cute problems. So example number 5 from your in-class problem packet simply states that Kc is simply 49. We're dealing with a 450-degree system here. Equations down below, so they're going to give us some concentration data. We have 0.22 moles of I2, 0.22 moles of H2, 0.66 moles of HI, and we're in a 1-liter vessel. So luckily, all of the mole data that they give us, we can just use as molarity. And we're asked, are we at equilibrium? And if we're not, well, how do we get there? So what I'm going to do is take my equation and define what Kc would actually equal just by using the chemical formulas. So remember again, those coefficients do matter. So I have Hi squared divided by H2 times I2. Now Kc is going to be Q is going to be calculated exactly the same way, the exact same chemical formula. And again, the major difference between K and Q is simply the numbers we're plugging into them, where Kc is limited to equilibrium concentrations. They explicitly have to say this is at equilibrium. Where Q, you just plug in the concentration data that you're given, and it helps you make the decision about how to proceed. So I went ahead and I plugged in the data that they gave us, the 0.66 moles or molar for the Hi and the 0.22 moles for the H2 and the I2. And when I plugged and chugged that into my calculator, I got the value of 9. Now, Kc equaled 49. What that means then is that Q is actually much smaller than K, and we're not at equilibrium right now. In addition to us knowing that we're not at equilibrium, we know then that the denominator would be way too heavy. It's way too big to generate that small Q number, meaning we have too many reactants. So the reaction would need to move in the forward direction toward Hi, making more products to reach that equilibrium.